Okay, good morning to everybody. My name is Carlos Alvarez, and I'm going to present this word about how to enable parallelism from a high-level programming model in a multi-FPGA clusters in this talk, but I'm going to give some hints on how we expect to extend it to multi-whatever clusters. So this work has been done at the OMS at FPGA group at the BSC in Barcelona and at the Universitat Politécnica de Catalunya, and I'm only part of this, I don't know if large or medium group that is the one that has been developing everything. Okay, so what are we going to talk about? Basically, we are trying to move in a world where heterogeneous systems are everywhere. We have a lot of applications that need more performance, and the thing is that what we have been doing up until now, that it's extending SMPs, is not really working anymore. So we are going into a world where we need to get more performance, lower energy, and we are using things like matrix multiply accelerators, GPUs, maybe FPGAs, that it's what we are working with, but we need to deal with this heterogeneity and we need to try to do something out of it. We are interested in FPGAs because they are highly flexible, so we can do any kind or any type of workload. We can do very fine-grained optimizations. They are very power efficient, and also we believe that they are not so hard to program. That's something that maybe it's a little bit, well, let's see. However, the truth or the current situation is that FPGAs are still very hard to program. We don't have a mature level ecosystem that allows us to program clusters of FPGA, and we want to address this problem. In order to do that, I'm going to talk a little bit about history, at least BSC history. Here, everything started a little bit more than 10 years ago with OMS. We are currently working with OMS 2, but for the sake of this presentation, both of them work the same. We like to say that OMS is a forerunner of OpenMP, because the tasks in OpenMP have been a follow-up from OMS, but everything started with this maybe silly idea. We have here a Cholesky in blocks, a solver for the Cholesky system of equations, and we basically have these 4 functions that are typically what it's used in order to solve the Cholesky. Basically, the OMS idea was, okay, we can annotate every function with a task pragma, that's here. The task pragma also includes the parameters or the dependencies of the function that basically indicate which data is flowing into the function and which data is modified by the function and flows into a different function. And then the runtime, it's capable of computing this task graph on the fly. So we can say, okay, first we are going to do this first Potter F, then we are going to do these 3 TRSMs, then we have a mix of the gems and the circs, and so on. So basically, with this graph, we can get the parallelism that it's available at the task level in this problem. The thing about this parallelism is that, okay, so this has to be computed sequentially, but then inside, this can be computed by 3 different cores at the same time. This can be computed by 6 cores, and so on. There is a trade-off here. So if we have a fixed problem size, and we play with the size of these tasks, so we play with the block size, we see that as we move over there, we have more tasks. More tasks that are smaller. So what we expect is that if we here can get a parallelism of 6, if we move to a smaller block size, maybe this parallelism can grow up to 60 or 600 or 6,000, whatever. So what we will expect is, okay, if we have a lot of resources, we are going to keep getting better speed up. And this is what happens. This is what is being shown here. We move to a smaller task for the same problem size. We have more tasks and we have more parallelism. And if we look at the speed up, we see that the speed up is growing as we diminish the block size for solving the same problem. So that's great. Let's go to the minimum block size possible, that it's around 8 or 2. And what we see is that then the speed up starts dropping. Why? Because the problem is that here, these tasks are each of them so small that we take more time in order to distribute the work than in order to compute the work. I mean, if we are talking about a block size of 2, this is a 2 by 2 matrix multiplication. So it's ridiculous. So it's so small that we don't have we don't care about computing it. This is 4 by 4. This is 8 by 8. But depending on the different application, we see that we can go for problems that are rather small, or that after a certain point, we can really not go into smaller problems. So what can we do? There was a proposal, also nearly 14 years ago, that was try to do this in hardware. This proposal was, okay, get the task graph, compute it in hardware with this machine here. This is the task superscalar machine that was proposed. That basically I'm said, okay, let's try to get this speed up, make it keep growing, because this is hardware, and this is going to be done really faster in the hardware. Okay, and that's the point where we picked the thing. So this was already done, and when we reached this point, we decided that maybe we should do it in hardware. And we did two things, basically. The first one was take this hardware, design it here, and try to make it in hardware and make it work. And we analyzed it. It was really well done. It was perfect. It was fast, and it didn't work at all. When I mean it didn't work at all, I mean that it gets deadlocked. And that's it. So you cannot get nearly 4 or 5 tasks, and after that you are killed. So it didn't work. It was not possible to make it work. The problem is that this is very complex, and you need a lot of details to take into account, because things start flowing from one module to the other, and this flow often saturates the intercommunication queues that are here. And then you get things that this one is trying to write here, but this one is trying to write here, but this one is trying to notify this one, and that's it. And so on, it's happening everything. So we did the analysis. We saw that it was a great idea, but it was a great idea that didn't work. So the first work was we tried to make it work, and we designed Picos. Because in fact comes from nanos. So I mean, Nanos is the runtime organizer in software. Picos is smaller and faster, so it's the runtime organizer in hardware. Okay. So this is Picos. It more or less has the same module. So this is the TRS, the same. The ORT and the OVT are both joined together. They have different memories. The gateway is more or less the same. This part is the same, but this one is one. This one worked and was designed in FPGA, and we were able to make it work without deadlocks. So, okay, that's great. We have something that it's working for real in an FPGA that gets not deadlocked. So how are we going to test it? Well, if we have it designed in an FPGA, let's try to test it in an FPGA. So we got a Sync FPGA that I don't know if everybody of you knows about it, but basically it's a really small FPGA that has 2 ARM core processors attached to it, and that it's really simple to get up and running. It's very fast, it's cheap also, so we can pay for it, and we started looking at it. And we looked at what happened with a problem that it's executed in sequential, so with no task at all. With Nanos, with 2 threads, Nanos is the software runtime that is used in the 2 ARM cores, and also using Picos that it's in the 2 cores and the FPGA in this same board are closely attached, so they both can access the same memory. So we managed to put to make the 2 ARM cores work with the Picos subsystem that we designed. So it was a real hardware with Picos working in the FPGA, and we compared, and we get these nice results. Where for okay, this no, this is okay. This is the block size. So this one bigger, this one small. This is the time that takes the sequential code and the time that takes the software task parallelized version and the hardware task parallelized version. This sequential is running in 1 thread because it's sequential. So while these ones are using the 2 cores in the system. And what we see is that we have two behaviors. One is that at the beginning, the best thing is to run it sequentially. Why? Because if you run it sequentially, you don't have to create tasks, you don't have to delete tasks, you don't have anything to do, only run the program. So it's the best thing. And as you get the block size and you have less tasks and smaller, you start to get the advantage of the parallelization, and always the hardware part was faster than the software part until you reach the point where they are more or less the same. This is the blue line. The blue line is the speed up that you get of the hardware over the software. So as you can see, for these two, we have 1. So it's the same to use the hardware or the software. But we have this small place in the middle where the hardware is faster than the software, and it's worth it. And with this, we reached the point that we said, okay, this is perfect, we can simulate it. If we simulate it, we think that this is great if we had 64 cores, but this is the reality, we only have 2 cores, and what we can demonstrate is this. And it's great, we have demonstrated that it's faster, but only it's worth it for 1 block size. It's only 20% faster. If the block size is smaller, it's better to not parallelize it. If the block size is bigger, the software it's already done and works. So it's a great theoretical result, but well, the practical possibilities are not real. So the thing is how we can try to demonstrate that this thing is working better than the software counterpart in a practical way. So one of the problems was more or less technologically solved for us because this was a thing. After that, after these small boards, they came another boards that were not so small, that were the Think UltraScale Plus. The Think UltraScale Plus were basically the same boards with a little bit more of FPGA, but instead of 2 ARM cores, they have 4 ARM cores. So we could expand this to 4 cores. Oh, that's great, 4 cores. But, okay, that's great, 4 cores. 8 cores. Okay, maybe we want something more. And what we realized is that we had a lot of FPGA free in the system in order to do computations. Okay, maybe what we can do is, instead of trying to accelerate the cores, we are going to try to accelerate accelerators in the FPGA. So we basically implemented this in the Think UltraScale Plus. Basically, it's the same idea, but we have this Picos hardware. This is the same scheme as I have presented before. It's in the FPGA part. We have in main memory a lot of communication in order to communicate the cores with the Picos hardware, because both parts, the FPGA and the cores, can access the same main memory, so the DDR, without problems. We have the software stack that was already there, but what we did is add a lot of hardware accelerators in order to do computations. So we are not more limited by the 4 CPUs here, but we can put as many accelerators, as long as they are not too big, to be honest, but we can put a lot of accelerators here. And we did basically these experiments where we can reach up to 24 different accelerators. Okay? And we get these results where we say, okay, we have the speed up, so the bigger the better, in red of the Picos full system. That means this is really executing this part. We have the perfect simulator, the yellow line. This is the maximum speed up that we will be able to get, knowing perfectly how to distribute the task graph and don't taking any time in order to use it. So this is our theoretical maximum. And then we have the green line, that it's the Nanox runtime software, that basically is, okay, we are going to do the same, but instead of using this hardware part here, we are going to do these computations in software in the ARMs. That, by the way, are A53, so they are way out of order, I think, so they are not so small. And we get these results. So basically what we see is that we get, as we grow the number of threads, the results of the red lines for Cholesky, this is Sparsal U, and this is H264, the decoder. Basically what we saw is, okay, we can have, for real, some executions that are faster than the software, and that are, okay, reasonably close to the maximum theoretical speed up limit that we can get with this system. So the thing is working. Okay, but how we proceeded? after that. So the thing here, and I'm going to take a step backward here, is that we were already working in a completely different subject at this moment. That, or at least that was we think that it was a completely different subject that was about trying to program things on FPGAs. So in this different line, we started developing what now is called OMSAT FPGA. At this moment, it was called OMSAT Think, because remember, we only have these think boards, small think boards, so it was OMSAT Think. Basically, what was the idea? Okay, if you remember, here, OMS, it's basically about getting tasks and sending them to all the available computing resources in the system at runtime. What we decided is, what if this computing resource is not a core, but it's an FPGA accelerator? Can we use it with the same programming model? And that's what we did. So basically, we get this subcode that calls to a matrix multiply hardware system. This is the matrix multiply hardware code. And as you can see, it's a standard C code, except for this Pragma HLS lines here. If you have worked with Xilinx, no AMD FPGAs, HLS is the acronym for high-level synthesis, and is a tool from Xilinx that basically gets C code and generates automatically RTL code. So basically, we get this code that it's HLS code, we pass it through the Xilinx EDK, and we are able to generate the hardware. Okay, that's it. That's something that's done by Xilinx. But what we did is add this to this Pragma OMP task in and out that it's exactly the same as this one. In fact, it's not exactly the same because this is OSS because this is OMS2, and the other one was OMP because it was OMS1, but apart from that, it's exactly the same. And we added some clauses here that say, okay, this task is going to target the FPGAs and the SMPs. What does that mean? That we are going to generate two different implementations of this function. One that goes through the regular GCC and is executed in the ARMS, and another one that goes through the HLS and it's executed in the FPGA. So also, we are going to put here these copy deps. And that means, okay, also when you are going to send something to the FPGA, add some hardware here, so I don't care about copying A as an input and B as an input before executing. And also add some hardware, so when you have compute C, you copy it back to the CPU, so I don't have to care about this detail of I have to copy the data into the FPGA, I have to move the data out of the FPGA. I don't want to care about this, because it's always the same. I mean, it's a DMA mover, it's pretty simple, put it for me, okay? So that's basically it. We developed this thing, we added it in the Mercurium compiler. Mercurium was a source-to-source compiler that was developed at BSC at the moment. Now it's working with LLVM, so it's not Mercurium anymore, but this was the first implementation. And we did everything. In fact, with the time, we also did all this splitting and compilation and adding of the things. It's automatically scripted, but we keep developing the scripts. So basically, everything works together, and we call automatic integrator tool, but it's a collection of, well, highly developed scripts, they are not simple, that basically put everything together, and we have this working. This also works with this software runtime. There basically what we are doing is we have the application code, then we call the APIs. The APIs take care of the task management. The task management is done in software, is nanos. They do the dependence analysis. We manage the data coherence, that means the data copies. We also do the thread management, that means when after we have done the data copies, we start the thread that has to do the work, and then we are able to send the task to the threads and deploy it over any underlying software, hardware, sorry. Hopefully, so we have the SMP part, that was the original one. We have the GPU support, so we can send tasks to GPUs. We have the FPGA support, so we can send tasks to FPGAs, that's the part that we developed. We also have cluster support, so OMSAT cluster comes from here. And that's the idea. And that was the results that we were having at the time. Remember, sync, ultra scale, so small FPGAs, only 2 cores, A9, in fact. So small board, small FPGAs, small SMPs, but we have the same execution in one SMP. So this is a trace, so this is time, and the different colors indicate the different actions that we are having in the program. So basically, these green colors here, the light blue, it's doing nothing. The green is also finishing, so also nothing. These purple lines are the task creations, so we are creating the task here, and these yellow lines are the task execution. So here we are doing the computation. This is a matrix multiply. If we execute with one SMP, we have this, but if we execute with the one SMP and 2 accelerators in the FPGA, the time is the same, so we are taking a lot less time, so we are improving the performance. We have also the task creations in the SMP, but here in the FPGA, we are computing a lot of matrix multiplications. The red lines here are the same as the yellow lines here. So basically, we are doing the matrix multiplications in 3 places at the same time. In one SMP and in 2 FPGA kernels. And that's basically it. So we developed the thing worked well, and gave us this kind of results. So we have this compilation that it's one-line compilation. So from this, we trigger the whole system, and we get both executables, the ELF in the SMP and the bit string in the FPGA, and also from one compilation, so with one line, we can execute in both without doing anything more. Well, in fact, there is one line missing, that it's loading the bit stream in the FPGA, to be honest. So the load bit stream was not integrated in, it could, but it was not integrated. And also, this allows us to have this kind of results. So we have the manual version, that is the blue line, and the red version, that is the ohms line, and we can execute in one SMP, in 2 SMPs, in one accelerator, in 2 accelerators, or in everything at the same time. We developed manually the 1 SMP, the 2 SMP, the 1 accelerator, and the 2 accelerators version, but we didn't develop the heterogeneous one, because to do this by hand, it's really tough. However, using the runtime, these are 4 different codes, manually developed. These 5 lines are one single code executed with different parameters. And the system was able to adapt itself to the different situations and get the results. And of course, the heterogeneous computation was the fastest. So that was the other thing that we were developing. Basically, how to easily execute accelerators into FPGAs. Okay, so once we have reached this point, the thing is, how can we try to improve that? And we realized that in fact we were doing the same thing twice, because here we have all this task management, data dependence analysis, and data coherence that is done in software, but however, here we are doing it in hardware. And in fact, it was being done in the same board. So next big thing was, okay, what about if we integrate both of them? And that's what we did. We developed this system where we integrated Picos with OMSAT FPGA. It's this system here. This is only Picos, but we have a lot of cues from the accelerators, from the cores, so we have everything. It was better deployed because we were able to target things ultra scale, but also alveos that are PCA attached FPGAs. So we were able to execute in the x86, send the commands through the PCE and get things executed in the FPGA. And we get this kind of results. So this is an embody code. This is the embody that basically calls the calculate forces and rotate particles functions that are also here. And the novelty is that as we have everything like this in the FPGA, we can do this embody function in the FPGA that calls these calculate forces and rotate particles that are also on the FPGA. So everything is in the FPGA. We send to the FPGA, compute the embody, and then one accelerator in the FPGA, it starts creating this task. This task goes to Picos, that it's also already in the FPGA. It sends back the task to the other accelerators, to the corresponding ones that are in the FPGA, and we are able to compute everything in place. So we have this kind of results. So this is the default. The default is basically using these boards and using this system here. So we compute everything from the host, and we call the functions in the FPGA. We also did some memory optimizations that I have selected the embody here because for this particular kernel, the memory optimizations are not grid. We have other kernels where they are grid, I mean matrix multiplication as an example, that we have already tested, but for embody, these are not grid. But for this particular application, the idea of having everything inside the FPGA was really grid, both for the simple ultra scale, so a small board, FPGA and CPUs attached, small CPUs, and an alveo that was in fact big board PCIe attached with high or big x86 host kernels, sending three things through the PCI Express, so a large communication path between. So that's great, it works fine. And in fact, at the moment, in this moment, this was the fastest embody implementation that you could get in CPUs or FPGAs. So that was a really great result at the time. We believe that it was the fastest embody implementation also if we take into account GPUs, but that's not true. So if we take into account GPUs are still able to beat us, and get more speed. But nevertheless, it was great because with one Alveo we were able to get the performance of 2 or 3 x86. So it was using basically 1/10 of the power. Okay, so that's great. We have done it. Everything is working. We are great. So HPC, it's solved. Wait, HPC, high performance computing, one FPGA. When I take these numbers and presented it to the software guys and said, oh, this is great, we hardware guys are the best, you software guys cannot do anything because we are 3 times faster. They say, okay, I'm going to put 10 processors in a cluster and that's it. Maybe you have a point. Okay, so, okay, we have this. What we want is to be able to exploit this over a cluster of FPGAs. So we have to move to a cluster. How do we move to a cluster? Well, if you have a cluster of SMPs, what you do is use MPI. If you want a cluster of FPGAs, what you have to do is create an MPI for FPGAs. And that's what we implemented. OMPIF. OMPIF, it's OMS MPA for FPGAs. So, okay, it's basically a hardware runtime where we have these calls called OMPIF send and OMPIF receive that are similar to the MPI send and the MPI receive calls because we basically cloned it. And we tested them in a cluster of FPGAs. I'm going to talk about this cluster later. But we reached a cluster of FPGAs that were available to us, that it has in fact up to 64 FPGAs that could work together. But we tested it with 16 at the beginning, and we programmed the same embody, the same that we are using here, because we already have it, and we are programming it from high level. So, I mean, we get the C code, compile it with HLS for the new FPGA, and that's it. It's very easy for us to move from FPGAs. So, we tested it in these FPGAs, and we get this kind of behavior. So, we have 16 FPGAs. We deployed the system from a host CPU, and this system is particular because everything is network attached. So it was developed by IBM, and the CPU is attached to the network, but the FPGAs are also attached to the network. They are in a rack, but they are isolated. They are not directly connected to any CPU. They only work as network things. So you can send things to them through UDP. So with this MPI send and MPI receive, we developed everything, and we saw this curve here. This is as the problem grows. This is the GPP, so gigapairs per second, is the same as here. But as you see here, with one FPGA, we were reaching nearly 40. And here, with 16 FPGAs, we are reaching nearly 30. What's happening here? What's happening here is that basically the host, the CPU host, was the bottleneck, because we were saying, okay, this FPGA, compute the update particles, compute the update forces, now send the data to the other FPGA at the site. But in order to send the data is, give me the data, I send it to the other FPGA. Give me the data, I send it to the other FPGA. So, okay, the copies to the CPU are the bottleneck. We are going to implement a direct copy from FPGA to FPGA. And we did. and it didn't work. So we have this green line where the copies are from FPGA to FPGA, but okay, at the beginning it seems to work, but at the end we get exactly the same result. It's not scaling at all. Why? Because the problem is not the copies. Well, the problem is also the copies, but it's not only the copies, it's the synchronization. We cannot have this system because the communication with all the nodes to the central node that is orchestrating everything, it's too slow. The problem is the CPU. The problem is not the FPGAs. The problem is the CPU. How do we solve the problem? Well, here we can see that the CPU was not the problem, but it helps to avoid the CPU and put everything inside the FPGA. We are going to do the same. And we did distributed. Okay? The distributed system is a new class of task that basically is sent to all the FPGAs. So we have this system where we have one main CPU, we have several FPGAs, and each FPGA has the same. The accelerators that it needs in order to compute the thing. This is the 4 accelerators and this rather strange graph because this is a Cholesky, but it's the same, could be the embodied. We have the on-PIF accelerators that is on-PIF sends and on-PIF receive, exactly the same. So the FPGAs can send data directly to one another, but also we have this distributed task accelerator. This distributed task accelerator basically means all the FPGAs are executing the MPI code that calls the on-PIF send and the on-PIF receive in the FPGA. So basically the core says to all the FPGAs, okay, this is your data, this is your code, compute it. The FPGAs start working together, and after they have computed everything, they notify to the main core, okay, we have finished, and then the main core can read the resulting data. That's it. Really simple, because we already have more or less everything that we need, except for the communication. And so that's what we did. Basically, we used the same FPGAs in the cluster, 16 FPGAs, and we have these results. That's what happens when we do everything. It's the same resources for the 3 lines. So it's exactly the same resources, and we are trying to do our best. But basically, if we use the FPGAs without the central CPU, we get rid of the bottleneck. The FPGAs do everything by themselves, and as soon as they have enough data, they get the maximum speed up. They cannot get more gigapairs because they are Kintex ultra scales, so they are not so big, so they individually, each FPGA doesn't get so good results, but altogether can get nearly the maximum that for this one it's 100 gigapairs. Okay, so maybe we should test it with all the FPGAs in the system. And we did. We were able to execute up to 56. The system has 64, but it was not really reliable. This is an image of the system. So this is the rack. These are all the FPGAs put together, and these are the connectors. So, and that's it. That's basically the system. There is no CPU here. Out of the 96, it's 3 racks. This is only 32 FPGAs. We can only use at the same time 64, and out of the 64, 2 or 3 were always failing, because maybe the connection was not good, or the bit stream was not properly loaded. It was really tricky to work with this system. It was a really experimental system. But so we settled for 56 FPGAs, but with 56 FPGAs, it's okay and it works well. This is the ideal scalability, and this was what we were getting. 350, near ideal scalability. And this is the thing. We have this code that is the same embodied code that we have seen before, but with all the MPI-like calls that also put us an explicit, an implicit barrier here. So we have to do this, interchange all the data, and then do another step. But everything is done in all the FPGAs, and this index, these different indices here, basically take care that the FPGA is only computing its own part of the code. So, well, let's say that that's it. Let's evaluate this thing, because embody, it's okay, but it's not so great, but we can try to do some things. So we have evaluated it in 3 different systems, and they are really different. One is the cloud FPGA. That was the one at the beginning. It was owned by IBM Zurich, and it was a cluster of basically 96 Kintex UltraScale standalone FPGAs. So basically these ones here. It's a small FPGA and it has not so big memory. Also the network was, good. We have UDP and TCP internet protocols, but we stick it with UDP because it took less resources out of the FPGA, and as the FPGA was not so big, we wanted to have something in order to compute. But it was great because it allowed us to start the system. But after that, we wanted to test with a bigger FPGA. And when we could get our hands on was this, or not exactly our hands, let's say our terminals. It's this Esper cluster. This Esper cluster is part of the Fugaku supercomputer. It's hosted in Riken, in Kobe, and basically features 8 Intel nodes with 2 FPGAs each. These are Altera, so Intel FPGAs. There are Stratix 10, huge, and we have this 100 gigabytes network, 16 gigabytes of memory each, and also we have this communication here through PCI Express. So we basically implemented, adapted our system to the network that they have implemented. This network communicates the FPGAs directly, and we adapted our system more or less manually. This is not automated. So each FPGA server can update all the FPGAs using the Riken tools. So we have this board where we have the IBM network and IBM tools in order to manage the FPGAs. And in this role part, we put our system. We have this system where the network and the tools are from Riken, and in this part, we put our system. And then we get our hands, and this time I mean our hands, in this mid-cluster architecture that was part of the Mare Nostrum Exascale project. In fact, it's a cluster that's not thought to do what we are doing with it. It's thought to do prototyping. We are using it for both things. So we are using it for prototyping, but we realize that we can use it to compute. And this cluster, it's really good for us because it has 96 alveos, U55, so big alveos. We have 12 Xeons, so each Xeon has 8 alveos of its own, and the Xeons also have 256 gigabytes of RAM, so we have good hosts. And we have 2 NVIDIA switches, so 48 FPGAs are connected to one switch and 48 FPGAs are connected to another switch, and they are both connected between them, so you can communicate from each FPGA to the others. And the thing about this system is that as this is an BSC in-house system, we developed everything for this system ourselves. So we can take it, we can publish it, we can share it, and we can distribute it. And that's what I am going to explain right now, how we implemented the hardware part of this system that we are using. So it has basically the same functionalities that we are using here and here, but these ones are not developed by us, and these ones are developed by us. So basically this is what we developed. So these boards doesn't have DDR, they have the HBM, but up until now we are not using specifically any capacity of the HBM. So the only difference between HBM and DDR for us is that DDR has 512 bits and HBM has 256, and we solve it basically saying, okay, the part with the HBM goes at 400 megahertz, the part that it's reading and writing to the network works at 200 megahertz, and so we have a width converter here, and 2 cycles at 256 give us 1 data and 512. And that's it. So we avoided the problem, to be honest. We have the accelerators that are generated by HLS with this copy data code that we added. We have the hardware runtime, that it's the one that we developed when we started to do everything in the FPGA. And we have also a packet decoder, a message receiver, and a message sender that is developed by us and that works with the Ethernet. Basically, what we did here is, okay, whenever we have to send some data, we send it to the message sender. The message sender basically reads the data from the HBM memory, and as soon as it gets the memory, it adds the ONPIF header. The ONPIF header is the minimum information that we need in order to say, okay, this data comes from this FPGA to this FPGA, so the ONPIF, the MPI-like call can map, okay, this packet is for this MPI receive. This is the information, and we send it to the Ethernet. In order to send it to the Ethernet, okay, we have everything here. We have the transmission, we have the receiver, and we have also the AMD Ethernet subsystem. This is an IP that comes with the FPGA, and that's what we use in order to communicate with the QSFP. We are using only one of the 2 connections of the QSFP. It's bidirectional, because in this system I has not mentioned it, but basically all the FPGAs are connected to the switch through one of the connectors and to the network FPGA through the other connector. But we are not using this other connection, so we are only using one of the QSFP connectors. So we use this to send and receive everything, and basically we have also a Ethernet header realigner and table. The idea here is that through the Ethernet we have to send fixed size packets. So basically we get the message that we need, we divide into different packets. These packets are 1,400 bytes each. We add the header, and then we add the Ethernet packet to the Ethernet IP, and we change the address to the MAC address that we have. So we have a MAC address table, we have the MACs of the system in the FPGA. When the data is received, basically we take out this data and we reconstruct the package. This is saved in a VRAM memory because if you don't read the data, it gets lost. So this is really time fixed, so you have to do everything one cycle. But we basically accumulate the data in a VRAM memory, and then when the VRAM memory is full with the packet, we send it back to the memory of the FPGA, and from this point, we forget about it. And the receive is this one. So we get the packet decoder. The packet decoder goes to the message receiver, where we basically join all the packets, as I was saying, and then everything goes back to the HBM. It works in the same way as as MPI. So I mean, there are in fact two copies, one from the network to the memory, and then from the memory that it's a temporary buffer to the real place where the data should be. And this last copy is done by the MPI receiver, the on-PIF receiver, in fact. So we can have as many packets in flight as they fit in the memory. As these boards have 60 gigabytes of memory, this is not a really big deal. So that's the idea. And also, we have to add an ASIC message back to the sender, because one of the things that we have realized in nearly all of the systems is that whenever you put a switch, you are doomed. And what does it mean? It means that if we connect FPGAs to FPGAs directly, we have done it and have measured it, basically everything you send on one side is everything you receive on the other one. So you really don't need to take care about error control because you got no errors. So you get a perfect 100% reliable transmission line. Whenever you have a switch, there are problems. And there are problems means that some packets get corrupted or some packets get lost. So you need some kind of error control. And remember that we were working with UDP, not TCP/IP. TCP/IP has error control, so it can do it. But TCP/IP is too costly to put it into the FPGA because it takes too many resources. So what we developed, it's little bit more reliable UDP that basically every time it gets 3 or 4 messages, I think it's the current configuration, it sends an ACK, so you don't have, you can get retransmissions if something has been corrupted. And that's the idea. But you have to implement this. I was saying nearly everything because this happens with our in-house system, this happens with the IBM system, but we don't know why it doesn't happen in Japan. So maybe they implemented better the system. The system is smaller, so maybe the switch was overkill here and it doesn't have these problems. They know something that we don't know. I'm not sure, but the fact is that they don't lose packets. But it's okay. In all the other systems, we lose packets and we have to have this control here. And that's it. That's basically what we implemented, what we have on the hardware part. But we have also the software part. And in the software part, we have done the tools in order to manage the MIP system. Remember that for the other systems, we were using IBM and Riken tools. But now we are using our own tools. And we basically have I'm going to say 3 tools. The first tool is the manager. So how do we deploy our system? How do we program 64 FPGAs in order to put it? Basically, we have an FPGA manager that it's more or less like the MPI run system that basically has a local node that's running in the x86 client and a server running in all the other x86 of the system. So when we want to program, the local node, that is the one that is going to, where we are going to execute, where we are going to say run, basically programs its own FPGAs through the PCI Express and the JTAG, and sends a request to all the other nodes in order for them to program their own FPGAs. We are not going to use this communication for the computation. For the computation, we are going to use the communication from FPGA to FPGA, that it's a different network. But we need to do this in order to program the system. So this is a system that it's also, we are going to publish the code, if it's not already there. I don't know, because this has been, all of this has been published last week. So it's, we are still, but our plan is to put everything open source and accessible. And also we have the stack for the application execution, where basically we have, so how do we do the order in order for everything to be computed? We have the local node where we have the full stack, where the QDMA sends the, send the distributed task to its own FPGAs, but the distributed task, that's the one that is in the CPU, has to be sent through the PCI Express, sorry. So we have to send this task also to the other FPGAs, and they are not directly connected to this host. So basically it's the same trick again. Through TCP, we have a server, an exact server in all the other hosts that only gets, you have to send this distributed task to all your FPGAs, and this one is sending to its own FPGAs. So everything can start at the same time. And then the communication is going to be done through ONBIF, through the network that joins all the FPGAs. This is the ONBIF run, what I was saying. So basically, it's a tool, it's a script, let's say, that from a description that it's JSON. So, the first FPGA in the first node, it's going to use this bit string, and it's going to be the first FPGA, the rank 0. This second FPGA in the second node is going to be FPGA rank 1 with this bit stream, etc. Usually the bit stream, up until now, it's always the same for all of them. And so it prepares everything. And that's nearly it. Just one more thing. And the last thing is that with this system, we are able to execute and get the results that I presented a few slides ago. That basically we get this original code. This is the code that goes into the FPGA, so without changes, with the automatic additions that we have. We can put instead this code. That's basically the ONBIF code that should go to the FPGA. But the thing here is that, this system is really more complex. I know that I'm going back a lot. It's much more complex than this one. So we need something. But the thing is that it's not much more complex. It has more things. It has more details. But in fact, the essential things that you need to do in order to execute this in one FPGA with 8 accelerators, let's say, is the same that you have to do in a system with 64 FPGAs with 8 accelerators each. Only 64 times over. So why has the program to be different? Which is the point? The point is that here you really don't care about the memory. That's not true. Because here, we don't really care about the memory. But here, we are caring about the memory because everything is orchestrated from the CPU and copied to the accelerators. And it's a distributed memory system. The FPGA has its own memory. The CPU has its own memory and the FPGA has its own memory. So both of them are separated and we have to do the copies. Okay, the copy should be done through PCI Express and on the other side you are doing the copy through the network. Doesn't matter. I have implemented, well, we have not implemented, but we have implemented one network system for our own FPGAs, and we have used two different network systems implemented by two different companies in two different parts of the world, and everything works the same because basically it's get this data from here and put it here. It's nothing more. We don't care about the details. So why do we need a different source code? Our answer, or what we are trying to answer, is that we don't really need a different source code. So we propose this IMP. This IMP is basically implicit message passing, and basically this IMP code, it's exactly the same as the original source code. There are no differences. If there are differences, that I don't know how to copy and paste. Okay? The only difference between the two codes is the pragma. The pragma has been modified. We have more information. We have here this distributed, and we have here this data distributed. That basically the distributed says, okay, this task is going to be executed in all the FPGAs available. And this data distributed says, okay, this P is going to be copied, broadcast in all the systems. So all the FPGAs are going to have a copy of P. And this F is going to be block distributed. So each FPGA is going to have a part of the forces. Basically depending on the number of blocks and the number of FPGAs. That I don't care. I expect the system to know how many FPGAs it has, and from here compute how much blocks it needs to put in each FPGA. It's a division. It's a computer. Can do it. So the thing is that instead of using this ONPIF code, we are going to program the things using this IMP code. That's the same as the original. We don't need to deal with random sizes, so all these nasty expressions here are gone. And also, we don't need this explicit synchronization. Okay, this is an MP file gather, so you get everything. Why do we need an AL gather? When I'm going to compute something, if I don't have the data, what I expect the system is to do the copy for me. That is what I was expecting in the single node. It's exactly the same. So that's what we did. This, I think it's still not published, not even the early version, but has just been accepted for publication in future generation computing systems. So basically, what does IMP? Basically, IMP gets the whole graph. Remember that with the distributed task, we are sending the task that it's creating the work to all the FPGAs. And instead of having these complex ifs that say, okay, if this data is here, I have to calculate the forces, otherwise I have to send the data, otherwise, okay, this is part of the runtime. Why? Because the runtime knows where the data is. So if this data is mine, and the task that is going to use it is going to be done by the FPGA 3, I know that I have to send the data to this FPGA. I can create a send automatically. Also in FPGA 3, if I know that I need this data and it's not mine, and someone has to send it to me, I can do a receive, because I know that I don't have the data. So I can put a receive and then execute the task. If I don't own the task, and I don't own the data, and I don't need the data, okay, let's forget about it and go to the next one. And I'm doing this in hardware. that means that I can process a task in 10 cycles. So it's a problem that I have to process 100 tasks that I'm not going to care about? No, because I'm going to process them in 10 cycles that in fact are pipelined. So it's less than 1 microsecond in order to get rid of all these tasks that I don't really care about. I'm only going to care about the tasks where I'm going to have to do something. So I can create this split graph directly from the original code. In fact, what we are trying to do, and this is what we are working, we think that we are there, but we need to test it more. You know that bugs appear whenever you less expect them. Is that, okay, if I have the original code with the distributed, this original code should work. It's the same as OpenMP. Maybe the speedup that I'm going to get is not the best one. Maybe I'm going to have a better distribution than the fail behavior, but it will work. I will get some speed up out of it, and I will be able to get ordered underlying resources. Doesn't matter if I'm dealing with a cluster or not, because in fact I'm doing exactly the same that I was doing when I have only one FPGA. Okay. So that's what I'm going to present right now. What happens when we do this? And these are the results for the 2 earlier clusters. That's Esper and Cloud FPGA. So basically, we have the embodied results, where we have perfect scalability in both of them. These numbers for Cloud FPGA are only up to 32 FPGAs instead of 56. Basically, because the FPGAs have kept dying. So we don't have 56 FPGAs. This cluster is so old that it's not, well, it's dying. I cannot say anything more. But we have some results up to 56, but we cannot get them for all the benchmarks. So for 32, it's perfect. For the Esper cluster that only has 16 FPGAs, and only we can use 12 because only 12 are attached to the switch. Also, the scalability is perfect. We do the same for the heat algorithm, the Gauss-Seidel version of the heat algorithm. So we got not this perfect scalability, but it's really close. And also, we get the same for the Cholesky, that the results are not so good. But we can compare here our IMP system, that this is the IMP system programmed by a macho programmer, so someone who really knows how to do the things. This red line is not expected to be what everybody is going to program, but this purple line is what we are going to get with our IMP system programmed more or less how everybody will program it. And this, the good thing is that this is the usual MPI code for Cholesky that you can get out of internet. So the MPI code does not scale well, basically because he's only working on lines, so he's not properly spreading the data between the computing resources. But we can do it automatically and getting this thing. The reason why this doesn't scale so well is because in the Cholesky, that as you know is a very complex graph, we need to send data, the same data a lot of times. If you are not careful, you end up sending the same data to do the matrix multiplication 3 times or 4 times, in fact n times, to the same FPGA. Because you have to realize that you have already sent this data and this data has not been modified. And this is something that it's really complex to keep track if you are in a complex algorithm, in a complex graph. The thing about this one, that I'm not going to talk more about it, but I can give you the details later because I've already consumed enough time, is that it has a catch. In fact, it's not a catch. It's like a small table where it remembers which data has already been sent and it's not sending it again. This algorithm that it's really taught to program is where the programmer has analyzed the algorithm and decide, okay, and this data I know that I have not to send it, so I have an if in order to avoid the send. But this is really difficult, and this is really easy. Okay. The difference is that the catch is not perfect. It's limited to 128 entries, and so if you have sent the data more than 128 sends before, you forget about it and you send it again. Okay. That's the thing. So, great. But we also can evaluate in MIP, and as we are at it, we can evaluate it at Mare Nostrum 4. It's Mare Nostrum 4 because this was done before the Mare Nostrum 5 was running. Now it's running, but it was not when we did the work. So we have the embody, the hit, and the Cholesky. We have the ideal line, that is the green one. We have the scalability that we get in the FPGAs and the scalability that we get in Mare Nostrum using all the resources. So one of the things that we are getting is that we are more scalable than Mare Nostrum 4 because we are able to operate at a small size. We are able to get a smaller task running in parallel. That's the thing. Another of the reasons is that maybe we are not so performant. So what we also measure is not only scalability, but performance. If we look at performance, higher the better, we see that Mare Nostrum outperforms us. If we go for the Cholesky, we are doomed. But if we go for the hit or for the embody, the differences are not so evident. And if we look at the performance per kilowatt, basically we are beating Mare Nostrum in the embody and the hit. And we are close in the Cholesky. And the thing is that not only does this work on FPGAs, but these FPGAs are 16 nanometers. And Mare Nostrum 4 was 14 nanometers. So we are competing with a better technology, a better hardware than what we have. And we are already gaining. We believe, this has not been demonstrated, but we expect to do it, that we can already improve these numbers by a factor of 2 or something like that. So we really expect to beat them in this way. So to finish, at last, basically, we made one programming model to run the load, yet another programming model to run the model. Also, we think that we have demonstrated that high-level parallel programming with FPGAs can be competitive, at least if we are looking at the correct set of applications. We are never going to beat Mare Nostrum for the Cholesky, and even less a GPU. Okay, so this is clear. But there are areas where we can go for it. And we think that maybe AI is one of them. So we are going to work on that. Also, we have learned that we have the problem of the technology. When the Alveos were new, they were the latest technology. Now they are still the latest technology, but they are still 16 nanometers. So maybe we need 7 nanometers FPGAs, but we cannot make them out of nothing. So that's something that we have to take into account. Another thing is that FPGAs are great to test the real hardware. Everything started because we wanted to test some great idea, the task superscalar hardware, for real, and we realized that it didn't work. But it didn't mean that it was a bad idea. It was only bad implemented. And it was badly implemented because it has not been really implemented. So maybe implementing the thing and testing it for real has a lot of value because you can go ahead over there. You move to a different point and you see things different when you are there. And finally, and that's something that our group is pushing for, is that we believe that massive parallel systems, supercomputers, maybe even servers, still need more hardware support in order to do the operations. So not so much hardware in order to do the computations, but hardware that helps them do the computations that they need when they need to do them and orchestrate them. So that's it. Thank you so much.
Thanks, Carlos. That's a great talk.